Hi, welcome to part 11 of the video series about laws of motion. In the previous one, we have learned how to calculate the normal force for 3 different cases. In this video, we will learn how to calculate the normal force applied on an object which is in a lift. Imagine we enter a lift and try to go to a higher level. Let's try to recall the feeling we are experiencing just when lift starts to move upwards. We feel ourselves getting heavier. On the opposite side, at the instant the lift starts to move downwards, we feel ourselves getting lighter. Hopefully, examples in this video will set light to this phenomenon. In the first example, a lift is accelerating upwards at an acceleration of 2 meters per second square. The mass of the object is 5 kilograms. We start with solution by drawing a free body diagram for this object. By doing so, we isolate the object and make the solution to seem much easier. There are two forces applied on this 5 kilogram object. Force of gravity exerted on it by Earth and the normal force exerted on the object by the surface of the scale. According to the second law of motion formula, the net force applied on the object is equal to the product of the mass and acceleration of the object. As object moves upwards, we consider upwards as positive and downwards as a negative direction. We can rewrite the equation as normal force minus force of gravity is equal to mass times acceleration. Force of gravity can be calculated as mass times gravitational acceleration, which are 5 kilograms and 9.8 meters per second square respectively. As mentioned in the question, acceleration of the system is 2 meters per second square. After calculations, we can get that the normal force exerted on the object is equal to 59 newtons. By standing on it, we are compressing the scale, and what the scale actually reads is the force that is compressing it. By the Newton's third law, the scale is pushing back on us with the same force, which is the normal force we have just calculated. Even though it is a very confusing term, sometimes this force is also known as an apparent weight. I will not dive deeper into it as it may confuse most of us, but put simply, there are two types of weights. The first one is the actual weight, which is the force exerted on an object by a planet, and which can be calculated by multiplying mass and gravitational acceleration. The second one is the apparent weight, which for this type of questions has same magnitude as the normal force exerted on the object. In the second example, the same object is now in a lift which accelerates downwards. The task is the same, to calculate the normal force or reading on the scale. As usual, let's start by drawing a free body diagram. We draw the force of gravity and then the normal force. Then, to get our first mark, we continue the solution by typing the formula. Net force is equal to mass times acceleration. By convention, we will consider direction of motion as a positive direction. The system is moving downwards, which means for this question, force of gravity will have a positive value and the normal force will have a negative value. Force of gravity is mass times acceleration. After substitution, 5 times 9.8 minus the normal force is equal to 5 times 2. The normal force and the reading on the scale is going to be 39 newtons. The third question is the interesting one. Everything is the same as in the previous question, but the acceleration of the lift. This time, it has the same value as gravitational acceleration, 9.8 meters per second square. We will go through the same steps. Draw a vector downwards to represent the force of gravity, and another one upwards to represent the normal force. Then, to make sure that we get full marks, we will write down the formula. Consider downwards as positive as object moves downwards. Finally, we do substitutions. Mass of the object is 5 kilograms, and then both gravitational acceleration g and acceleration of the system A have the same value, 9.8. The normal force exerted on the object is equal to 0, which means the reading on the scale is 0 as well. The object is weightless, and this phenomenon is known as weightlessness. I pray that no one will experience it. The cables holding the lift are broken and it falls down with everything inside it. In that moment, objects will not be able to compress the scale, so the reading on the scale will remain at 0. We are not going to solve a question about it, but can you guess what will happen if the lift falls down with a greater acceleration than the gravitational acceleration of 9.8, let's say at 15 meters per second square? Yes, you are right. In that case, we will stick to the sailing. In other words, the sailing will become a flow for us and we will be able to walk on it. The next question is also a tricky one. We may get it wrong unless we read it properly. The lift is still moving downwards, but this time, instead of 2 meters per second square, the value provided is 2 meters per second. As we recall, meters per second is the unit of velocity, not acceleration, meaning the acceleration of the system is equal to 0. If we follow all the steps again, draw free body diagram, then write down the formula for the second law of motion, extend the formula by determining the downwards as a positive direction, and then do substitutions. The normal force is equal to 49 newtons. Let's finish this video by one more tricky question. A lift with a scale and object on the scale moves upwards, but at the same time it slows down. What will be the reading on the scale? We should already get used to starting to solve this kind of questions by drawing a free body diagram. Force of gravity is acting downwards, and the normal force is acting upwards. The lift is moving upwards, which means we will consider upward as a positive direction. The normal force will have a positive value, and the force of gravity will have a negative value. The force of gravity can be calculated as mass times gravitational acceleration. The tricky part of this question is hidden in substitution part. In grade 10, we have learned that if an object is speeding up, the direction of velocity of the object and its accelerations are same. And if an object is slowing down, the direction of the velocity of the object and its acceleration are opposite to each other. The lift is slowing down, which means velocity and acceleration are acting in opposite directions. We have already considered the direction of motion or direction of velocity as positive, which brings us to conclusion that the direction of the acceleration must be negative. You may ask why we didn't write minus in front of gravitational acceleration. We already did it. The minus in front of mass times gravitational acceleration belongs to g. As a result, the normal force is equal to 39 newtons. In this video, we have solved a lot of questions involving objects in a lift. In the next video, we are going to learn about the friction force, classify it as a static friction force and kinetic friction force, and at the end, we will define the coefficient of friction. Don't forget to subscribe and turn on the notifications in order to be updated about my new videos.